All right, so then let's go ahead and talk about operational amplifiers, or op amps for short. So the operational amplifier behaves like a voltage-controlled voltage source, and it can be used to perform mathematical operations. That's where it gets its name. Those operations can be addition, subtraction, multiplication. That's kind of the the gain structure we were seeing. Division. You can even differentiate a signal. You can take the derivative of a signal, or you can integrate a signal. You can find and produce a signal that is the integral of another signal. Isn't that cool? So anyways, there's all kinds of really cool things you can do with op amps. The standard package for an op amp looks like this. So you guys are in the lab, you'll be working with op amps next week. It's an 8-pin package. And that's often called a DIL package, or which stands for dual inline package. Or sometimes it's called a DIP package, which also stands for dual inline package. You'll see both of those names shown. This is the pinout diagram for the 741 op amp, which I believe is in your kit. It's an 8-pin device. You do not need all 8 pins to use it. In fact, oftentimes other pins are not used. Sometimes they are. One thing to note is that the op amp itself is a powered device. It requires DC power supplies. These DC power pins are shown. That's the schematic symbol on the left. Now on the schematic, these are not always shown. In fact, oftentimes, especially in a dense schematic with a lot of different components around, you won't see the op amps shown there. So if I was to pull up, let's say, the schematic for this, let's see if I can find this real quickly. Oh, yeah, here we go, DTs, David Thomas, there we go. Let's see if we can find the schematic. Here's the schematic. Okay, this is a project. I actually ended up building one of these. I built a few of these on a breadboard, and then ended up designing a PCB, and it's enclosed in a housing. It's in my back room. I use it sometimes. It's actually a compressor that's kind of tailored towards for vocals. Never mind what a compressor is. It's like an automatic level control. But anyways, take a look. It is a pretty comprehensive circuit, but you see all these triangles everywhere? Every one of those triangles is an op amp doing something. This one right here is doing an input stage buffer, essentially. This one here is doing a little bit of gain. This one here is actually, with these diodes in here, which we're going to look at diodes in the lab, this is actually taking the absolute value of the circuit. Anyways, you'll notice that you don't see the power supply connections on any of these op amps. You see pins 2, 3, and 1. Those are the inputs. 2 and 3 are the inputs. 1 is the output. But you don't see the power supply lines connected there. They've been left out for clarity. You do see, however, if you look on the schematic down in the lower left corner, you see here are all the op amps shown there, and then there are their power supply pins. It looks like they've been connected to plus and minus 15 volts respectively. And it looks like they put some capacitors in there, which we can talk about why you do that. And we'll take a look at that as we go into applications. I know what you're thinking. You're looking at this and this is like, oh my gosh, that's a ton of information. And also, how do I even analyze a circuit now that this triangular thing is in there? Trust me when I say that the triangle, every time we get to this point in the course in circuits, including when I took this class, at Kenyatta College a long time ago, when I or any student who's gotten to this point in the course, they get to the op amp section and this triangle shows up, and now you have to analyze circuits and there's a triangle in the middle of there. It always it's a point of confusion. It starts to feel like, oh man, all of the circuit techniques that I've just learned are now not as easy to do because of this pesky triangle that's in there. But trust me, we're gonna walk through the golden rules of the op amp and how you analyze it and how you use your existing circuit analysis techniques that we've built up to this point in the class to still analyze those circuits. And if you follow the steps, You can't go wrong. You'll get it right every time. All right. Let's take a look at some of the other pins. Here's some other pins on the op amp. This is VN. I'm going to write these a little bit bigger than what's on the diagram here. VN. That stands for the inverting input. VN is the inverting input. Okay, it often is shown with a minus sign like this on the schematic symbol. And on the 741, it is pin 2 on the device. So sometimes you might see somebody write the pin numbers on here, like this would be pin 2. The non-inverting input, which we refer to as VP, P for positive for non-inverting, N for negative for inverting. So this is the non-inverting input, and that's pin 3, right? And the reason that those inputs are termed inverting and non-inverting respectively, as you'll see soon, shortly, if you apply a signal to the inverting input, like let's say you put a sine wave into the inverting input, what you'll get at the output is an inverted version of that sine wave. So you'll get an upside down sine wave. The non-inverting input, VP, P for positive, if you apply a sine wave into that input, the output will give you a non-inverted sine wave. In other words, an upright sine wave that has the same phase as the inverting, or as the input signal. Okay, so the non-inverting input often has, in fact, not often, every time it has a plus symbol on the schematic. So if we were going back to look at this here, okay, and I'm looking at this input, I take a look here, I see, oh, here's the input coming through a 100K resistor, and take a look at that. It's feeding the inverting input of this op amp. That means I already know at that moment, and the non-inverting input is grounded. But trust me, by the end of, if not today, by the end of Thursday, I will introduce to you this circuit block right here between R1, R2, and this first op amp, and you will know what that does by the end of either today and or Thursday. And I know it looks like super complicated, but what we're going to do in this session is we're going to break down. And oh, I can't, let's see if I annotate on this. Here we go. And what we're going to do is break down the fact that those three components, R1, R2, and that op amp, they perform one function. That is a block. And in this case, it's actually giving a gain of -1, it turns out. And I'm able to look at that and say, oh, okay, that's what that's doing. I promise you by the end of Thursday, you'll be able to look at these blocks and say, oh, okay, that's giving a gain of -1. The input coming out of here, or the output coming out here, is going to be whatever this input signal is with the same gain. If it's a 1 volt signal, it's a 1 volt signal at the output, but it will be inverted. The phase will be inverted. So let's take a look at the last couple pins on the LM741. Pin 6 is the output here. Okay, so here's pin 6 coming off of that one there. That's V out. VO is the output. And then if we were going to draw on the power supply symbols, it looks like for the 741, this comes on pin 7. V plus, the positive power supply. V minus comes on pin 4. And so we would have then written down all the pins on the op amp package. For you guys taking the lab, when you're working with the op amp, you're going to have to pay attention to the pins, and so your wiring is going to become a little bit more complicated than it has been. This device is going to require, at minimum, what is it, five connections, 5 wires. You do have to connect the power supply to this. It will not work without the power supply. And an op amp, and in fact, any amplifier, is a powered device. You have to provide a DC power supply for it to do its job.